We're going to pick up right where we left off last week. We stopped right about here. We talked about albedo, which is how much light is reflected. And then our lab was trying to figure out how does the color of an object and the texture, the bumpiness of an object impact how much of that light is reflected or impact the object's albedo. So jumping in, looking back at what you should have found, which surfaces have a greater albedo. So for that greater albedo, that's going to be light-colored objects. So light-colored objects. And in particular, like ice and snow, we're going to look at this chart down here on the bottom right soon. Or maybe we do it right now, but fresh snow reflects 80 to 95% of the light. And so that's going to be light colored. It's white. Okay, so how might this affect a region's weather? So the effect on the region's weather, well, it's going to cool the air. And kind of the opposite of that, we said warm air expands and gets low pressure and rises, while cooling the air is going to be the opposite. That's going to give us high pressure. So how is snow in the winter time? A feedback loop. So what a feedback loop does is it something happens and it causes it to happen more, causes it to happen more, and causes it to happen more. So for us, that's what snow can do. So snow, we said, just cools the atmosphere, cools the air. So snow cools the atmosphere. When we have snow on the ground, so it's reflecting so much of the light, it's not making the ground warm. Well, that's going to make the air colder then. And as the air is colder, it's not able to hold as much moisture. So as it loses the ability to hold moisture, then clouds are going to form, and it could produce more snow. Unfortunately, that has not been the case this winter. It's been a disappointing winter. So why do you think cities are sometimes called heat islands? Well, if you look down here on our chart, down here at the bottom we have these dark objects, a dark roof and asphalt. Well, those there reflect only 8 to 18% and 5 to 10%. So say asphalt reflects 7.5%. Then that means 92.5% is absorbed. We know that absorbed energy changes into heat. So that's going to make everything warmer. So asphalt or pavement and dark buildings absorb, or you could say trap, the heat, as opposed to radiating it back off to space. So what could we do to avoid that? Well, we don't want the dark surfaces. So use lighter colored or even reflective. So I'll do comma, more reflective materials. So lighter pavement, lighter shingles, maybe you can get something reflective, or put solar panels on your roof. Then at least the absorbed energy is changed into electricity, so we don't have to get it some other way. Albedo values then, so looking over here, they don't really have the values, they just tell us the percent. We know these things are going to have a high albedo, these are going to have a low. So which surface is most heat reflecting? So fresh snow, and that's because it's white. And lighter reflects, lighter colors reflect. Which surface is most heat absorbing? That's going to be the asphalt or the black pavement. So it'll either be like black top, but it also could be like the really dark with like little tiny pebbles in it, so those make it look a little bit lighter overall. But that's because dark absorbs energy or absorbs light or something like that. Maybe I'll say light. Now the weird one, I don't know if you noticed this, is the water bodies. So this has a 5% range, 15% range, 15%, 10%, 10%, 5%. But the water bodies right there, we have this 50% range. So why such a huge range in water when we don't have that same range in the other? Well, if we flip over here, and this just shows the water bodies again, the huge percentage, and you get the dark roofs and concrete and whatnot. But for water, if the light's coming straight down, so when you're looking at a bigger angle towards the water, you're able to see easily down into the water. But for the light here that's coming and hitting the water, we can't see it. So that light that's coming there ends up reflecting back up into space. So if you have light that's more straight down, that is going to give you a lower percentage of reflected light. Light that comes in on an angle is going to be closer to like the 60% reflected light. So if I jump back here then, I could say, why not, let's go back to blue again. It depends on the angle. So it depends on the angle. And by that we mean more direct angles are reflected less. Okay, on to the top of the next page. We're talking about specific heat, which is a physics concept, so that gets me all excited right out of the gate. So the general idea for specific heat is we're looking at how much energy does a substance take to heat up or cool down. So a general idea, how much energy does it take to heat up or cool down an object? And I ran out of room there. Let me change the size here a little bit. So how much energy does it take to heat up or cool down an object? And kind of the graphic is talking about like an iron frying pan that's going to heat up really quickly because specific heat is smaller. If you have like an earthen pot, like a crockery sort of thing, that's going to take longer for it to heat up and cool down. Maybe that kind of fits with your experience, maybe not. But high specific heat, so something that has high specific heat, like this earthen pot, it's going to be harder to heat it up and cool it down. So I'm going to say high specific heat takes more energy to heat and cool. So you have to put more heat into it to warm it up, but it'll stay warm longer because it has to lose more energy to cool down. So the official scientific definition is it's the amount of heat, and that's measured in calories, that it takes for 1 gram of a substance, the amount of heat in calories that 1 gram of a substance must absorb or lose in order to change its temperature by 1 degree Celsius. Okay. And it kind of works both directions. So when something absorbs, its temperature goes up. When something loses energy, its temperature goes down. So it kind of works both ways. High specific heat, slow to heat up, slow to cool down. Low specific heat, fast to heat up, fast to cool down. An example from that is water and sand. I'm going to flip ahead to this here. So maybe this has kind of been your experience. I know I've had it before. And not the first slide or two, but it says, Hobbs, you didn't bring your swim trunks here to the beach. No, I prefer furry dipping. So if you haven't read Calvin and Hobbes, Calvin is a young boy who's crazy into mischief, and Hobbes is his pet tiger, his stuffed tiger, who he sees as alive. So they go to the beach with their parents, and they're running for the beach, get to the sand, ow, 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 ah. You know, that sand is super hot. They dive into the water, and the water's cold, and they run, ah, ha, 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 ha. And it's, don't tell me we drove an hour and a half for this. So they want to go home already. But the real point is sand heats up really quickly. You can go to the beach and the sand is like blisteringly hot. It has a low specific heat. It doesn't take much energy to heat up the sand or to have the sand cool off. Water, on the other hand, has a high specific heat, so water is really slow to heat up and cool off. So example, water. For this, I'm going to change this sentence a little bit because it's a little bit kind of janky. I'm going to say water, 1 degree Celsius temperature rise, when, so instead of needed for, when 1 calorie of heat is added to 1 gram of material. So if you take 1 gram of water, or 1 cubic centimeter of water, 1 milliliter of water, if you add 1 calorie of heat to it, it's going to go up 1 degree Celsius. Sand, on the other hand, is a much bigger change. So sand, if you have, so I'm going to take the when when 1 calorie of heat is added to the same volume of sand, instead of just going up 1 degree Celsius, it goes up 5.2 degrees Celsius. So sand heats up 5 times faster, given the same amount of energy put in both, than what water does. So water takes longer than sand to heat up, but it also takes water longer to cool down. Maybe you've experienced that at night. You know, the water temperature doesn't drop really fast in the lake, and you could argue it's somewhat because of the depth of the water as well. There's more water there. But the sand cools off a lot quicker. The sand gets cold shortly after sunset, or even before sunset, as the sun's rays are more on an angle. And because water doesn't change temperature real quickly, but sand does, that's going to give us a couple different kinds of breezes. So during the day, we have what is called a sea breeze. So I'm going to switch back to blue. In daytime, we have a sea breeze. And often they find this like near the lake shores, like Lake Michigan, bigger bodies of water, oceans, things like that. And what officially happens is the land warms quickly. And when that happens, we know the air above the land, that's going to expand. So as the air gets warmer, land warms, that warms the air expands, and then it's going to rise. And because of that expanded air, we have like a low pressure system. So right here, we're going to have, I'm going to say hot. So this here is daytime. So we're going to get hot, so that's going to give us low pressure, and that air is going to go up. Well, compared to that, out on the water hasn't warmed up as quickly. So I'm going to say the cool air above the water. We know cooler air has high pressure. And so then over here I'm going to have high pressure. Maybe I'll switch to red. So I have high pressure. And we know that areas of high pressure push towards areas of low pressure. So if you're the person here on the beach, you're going to have the air coming from above the water blowing towards you. So during the day, when the land gets warmer, you're going to have this air coming on land. So you'll have a breeze that's coming towards the shore. Yeah, I should finish off my sentence. So we get high pressure, pushes the air toward the land. Now night, we're going to have the opposite thing happen, because just like the land heats up quicker, the land is going to cool off quicker. So at night we're going to have what's called a land breeze. And I'm going to say the water stays warm. And that's because it has a high specific heat. Remember, that's saying it takes a lot of energy loss for it to cool off. And the land cools. And we know then that that's going to make the air cool. So cooler air, which gives us high pressure. So over here I have cool. It's going to give me high pressure. And that high pressure is going to push. So over here we said I have the warmer, which then is going to give me low pressure. So there's less air there. That warmer air is going to rise, and the high pressure is going to push air towards it. So the high pressure pushes air toward the low pressure above the water. Maybe I'll say above the warmer water. So those two things are kind of in conjunction with each other. They're opposites of each other. Lake effect is going to be a different sort of thing. Now on to lake effect. Lake effect, We have a couple pictures that kind of go along with that. One you can see on this slide, but I'm going to jump over a page. So I have this really slick drawing of Michigan here. And for us, we're going to look at 3 cities. We have Milwaukee, their precipitation. That's over here on the west side of Lake Michigan. We're here in Grand Rapids. We have Detroit over here. And the wind is typically coming from the west. We have the westerlies. We saw that earlier in the notes. And as that wind is coming, then it hits Milwaukee first, and then it goes over Lake Michigan, then crosses Grand Rapids, and then goes to Detroit. What we're going to find is with this lake effect snow, Milwaukee is going to be over here, kind of on this shore of Lake Michigan. So the west wind comes, goes over Milwaukee, and as that cold air moves over Lake Michigan, the water stays warmer because it has a high specific heat, and that causes some evaporation into this dry, cold air. Then that air rises as it's getting warmer from the lake water, and as it rises, it expands. It can't hold that moisture. The moisture condenses, and we get lots of snow, which shows then why Milwaukee has 34.5 inches of snow. Grand Rapids, we're almost 4 inches higher than that, and in honesty, like over by Coopersville, there's even more than Grand Rapids. But then Detroit, once it goes across the state of Michigan, it has even less snow there. And as long as I'm on this page, I'll see if I can get this to play. Sometimes that's a little bit messed up, but I have a web page here. This shows kind of Buffalo, New York. Come on, baby. This shows Buffalo, New York, where it has, you can see these clouds rising and so on. There we go. So you can see this lake effect snow as the water, as this air is coming over, you get a little bit of rising of the clouds. So like right here, we can see all these clouds forming. It's going to dump snow like crazy there on Buffalo, New York, just like it does in western Michigan. All right, let's write all this down and then keep going. So the lake holds the heat. So lake holds the heat. And it stays, you could say, warm longer. And like I mentioned before, that comes from its high specific heat. So here we have west winds. At our latitude, we have the westerlies, and that brings dry air over the warm water. And because that air is so dry, we're going to get water evaporation. So water evaporation from the warmer water adds moisture to the air. And when that happens, our air rises because the air is getting warmer from that warm water, and water vapor condenses. And that's going to give us clouds. And then as the air hits the land and cools off, the cooler air now can't hold the moisture, so it's going to drop it, and we get precipitation. We get our snow. So cools again. That's the air cools again over the land, and we get precipitation. Hopefully snow, but we get rain and that kind of stuff too. Okay, flipping over now to, already looked at that stuff. We jump up here to water versus sand, ocean additions. So how does this affect coastlines? Well, water has a high specific heat, so it doesn't want to change temperature very quickly. We already talked about sea breezes, where this air comes onto the land. And then at night, you'll get your land breezes where the air goes back over the water. But because that water doesn't change temperature very quickly, it's going to have a real moderating effect to the temperature. So I'm going to say water has a high specific heat. That's a theme that's coming back over and over and over. I think you'll see that showing up on the test. But because it has that high specific heat, we know it's slow to warm. But it's also slow to cool. It just takes a lot of energy absorption to make it hotter. It takes a lot of losing energy to make it cooler. So oceans then are going to stabilize. Ooh, that's ugly. Oceans. I'm just going to erase that and start over. So oceans stabilize the temperature. Abbreviate temperature just with temp. Or if you wanted to, you could say we have smaller changes in the temperature. So you take some place like South Dakota, it's not anywhere close to the ocean or even Lake Michigan, so it's going to get just brutally cold in the summer, but it's also going to get a lot hotter. I'm sorry, brutally cold in the winter, but it's also going to get a lot hotter during the summer because it doesn't have the water to regulate it. Okay, on to ocean motion, and I'll switch to purple. Oceans are a major driver in distributing heat. And this thermohaline, so thermal, see if you can fit it on there. Currents are driven by differences in density. And we're going to look at two different things that cause changes in density. First, thermal is going to stand for temperature. So temp or temperature. And we know that cold water, just like cold air, is more dense. So cold water is more dense. And when it's more dense, it's going to sink, just like the colder air sinks in high pressure systems. And then the haline, that's looking at like salt or salinity. The oceans are salty, Lake Michigan is not, but some places in the ocean have more salt than others. And just like cold water is more dense, salty water is more dense. So when the water's saltier, it's going to sink. And that causes us to have these different currents. And so if you remember Finding Nemo, where they talk about the East Australian current, the EAC, they get those sort of things happening. That's sometimes you find them labeled. It's probably this one here, warm surface water, kind of going towards the east, or from the east. But you get these currents moving up this coast of the Atlantic, the eastern coast of the United States. You get warm water moving up there from the Gulf, and there's these currents kind of taking water kind of all over. So oceans are ginormous. They have almost all the Earth's liquid water. So for contributing moisture, oceans hold 97% of Earth's liquid water. And because most of the water's there, you're going to get most of the evaporation as well. So most of Earth's evaporation. So most of what we get in rain and snow around the world comes from water that's evaporated out of the ocean. All right, so clashing air temperatures. First we're going to look at fog. Maybe you have seen those around on cold mornings in particular. So fog is when you have a cold air mass, so a cold air mass. By air mass, we just mean like a big section of air is going to get trapped under a warm air mass. And the dew point, that's going to be the temperature that the air can't hold all of that moisture anymore. So as the temperature then drops, as the temperature nears the dew point, that's going to be temperature nears the dew point. And then when that happens, that's the temperature where water droplets condense. So they go from evaporated moisture to actually liquid. If I jump ahead a picture, we can see, if I get off that video, okay. So this here is South Africa. They have a place where we're getting a cold current that comes in, and we get a warm current that comes in. And as those two mix, it's an area that's known for being really foggy. That's the Mingula Current in southwest Africa. So that's going to be one sort of thing. We can also see where we're getting mixtures of two different things here along the eastern United States. We have Florida and kind of moving up the coast here. So we have this Gulf Stream where we're getting this warm water that's coming up. We're getting this cold water that's coming down south from further up near the poles. And you can actually see where there's this weird swirling as these two things are mixing. That, I think, is just kind of cool. All right, so tropical storms. So we're talking about hurricanes and cyclones and typhoons, and what they're called is based on the area. So you see over here in the Pacific, they call them hurricanes, kind of the North Atlantic, same sort of thing. But over here in the Indian Ocean, we're going to have cyclones, and kind of that western Pacific, the other side there, we get typhoons. So it just kind of depends on the area for what you're calling it. But what causes these? Okay, so water we know has a high specific heat. And that allows it to hold and transport massive amounts of heat energy. So water has a high specific heat. That's like the fourth time we've written that. That baby should be on the test for sure. But because of that, it's going to hold. So holds and transport massive, ginormous amounts of heat energy. Okay, and by the equator, we have warm water, and now from that, you'll notice a lot of these things here, these hurricanes and cyclones, they kind of start down by the equator. So when you take that warm water and take it up towards polar regions, towards cooler places, so currents take the warm water to polar regions. As we're getting that warm, humid air from the warm, humid water that's moving, suddenly now getting into colder places, it can cause instability, or can cause, I probably should say, causes atmospheric instability. So it makes the air, makes the atmosphere unstable. And when we have unstable air, it can give us those hurricanes and cyclones and things like that. I think I need to go one more slide. Yep, so here I got a couple pictures for you. So you can see the hurricane, the spinning. You get the eye of the hurricane. You remember that song from Hamilton, great song. But what's happening is, as we have this warm air rising, it starts to spin, and that's going to be in the eye. It's kind of that middle part where you have the calm. And as it's rotating around, we're getting these convection currents in the middle. You get the hurricane winds from the rotating, and it's just huge. So I thought this was kind of a fun, if you're not in it, a fun analogy maybe. So if you take that wind energy, plus the energy that you have like stored up in the clouds and rains, it's this many watts of energy. It's sometimes hard to picture like times 10 to the 14, so 6 with 14 zeros after it. That's an equivalent amount of energy to 10,000 nuclear bombs. Fortunately, it doesn't have all that radioactivity that goes along with it. It's just a huge, massive amount of energy stored up in those things. Alright, so we're up to our last page here, valley and mountain breezes. Not as much writing, I don't think, as on the last one. You'll notice some similarities here. Looks like I need to make my page a little smaller. Some similarities in the pictures is what we had with the land breezes and the sea breezes, is we have this cycling air. And so valley and mountain breezes is going to be this top one. So first thing I want to point out is we're talking in this top picture about daytime. It's daytime. And when we have that, this land here is going to rise. We have warm air. Let me jump to the writing. So mountain air heats up more quickly. I'll say faster than valley air. So it's similar to when we had the land breeze. We had the land, this air heated up quicker, so it rose. But now we have kind of the land on both sides. This is kind of like the water in the middle. When we have that then, so we're going to get like a low pressure here. It's going to make the air go up. We have a low pressure here, makes the air go up. Maybe I should have copied what they did and did like red, showing that it's the warmer air. So we have warm and warm. Really, it's kind of all the way up is all warmer. And then when we have that, we're going to get this higher pressure comparatively in the middle. That higher pressure is going to take, I should have put my H up there, but the higher pressure is going to go and push the air towards those low pressures. So we get the cycle thing. So this is really similar to a land or an ocean breeze. So similar to land breeze, ocean breeze. Because this picture is similar to the ocean breeze, but if we look at night, it also, the mountain air cools off faster. So when we have that, then what am I doing? So this here is, so this is night. Looks like I covered it up right here. So this is going to be what happens at night. So this air cools off faster, which is going to give us high pressure because we get cool air. We have cool air here, it's high pressure. And then this middle air is going to be low pressure. We know low pressure rises because it's a little bit warmer. It's going to be more expanded. It's going to rise. And this high pressure air comes swooping in behind it. All right, rain shadow. So rain shadow, get a ton of that out in California. And let me write it first and we'll kind of pick it apart a little bit. So air rising up a mountain. So air rising up a mountain causes moisture to condense. And that's going to give us precipitation. If you think about low pressure near the equator and Hadley cells, this is the same sort of thing. But if we look at this picture down here, we have the air coming in. So think of out by California, we have wind coming out of the west off of the Pacific Ocean. And as that air comes and hits the mountains, it's forced upward, kind of like by the equator where it goes up because it's warm. But as that air gets forced upward, that causes the moisture to condense. As the air cools off, it can't hold as much moisture, so you get the clouds and you get the rain or the snow. And you can see that here, all the green in California is kind of right here along the edge. You can see you have like a mountaintop range where you're getting snow in the mountains. But then once you're past that, the backside, so it's lost its moisture, kind of like the top of a Hadley cell near the equator. Then it comes down dry and gives you like the Sahara and Mexico where it's dry. But now instead the air keeps going and the dry air comes on the other side. So our western United States over here tends to be really arid, really dry. So dry air on the backside of the mountain. Or maybe you could call it the leeward side of the mountain if you're familiar with that. And the example, you don't have that picture, but you could if you wanted to say Sierra Nevada. That's the mountain range in California, kind of like over here. I guess you don't have the picture. That's not helpful. And like Death Valley is really low. It's going to be really hot and really dry. All right, very last thing, volcanoes. Volcanoes, they're going to emit all kinds of ash and gas into the atmosphere. So ash and gas is released when we have a volcano erupt. Maybe you've heard about cloud seeding, where they put stuff in the air to try to get water vapor to condense on little particles in the air. But that, we'll call it just attracts water vapor. What it's doing is it's giving the water vapor that's in the air something to condense on, to turn into a liquid on. And that's going to cause rain, and you can get lightning. And where you have lightning, you have thunder. Feel the thunder, lightning. Okay. Other stuff that goes up, the ash and sulfuric aerosols. Think of sulfuric gas, kind of the smelly stuff. Aerosols are like really tiny particles. Those are going to block the sunlight. I'm just noticing my picture is there. We need to get rid of that guy. So in my diagram, we have a volcano erupting, it's going up, and then the wind starts taking these like aerosols, these little particulate matters off to the side. And when that happens, the sunlight hits those things, and some of that sunlight is reflected back into space. Most goes through, it's not like it's dark on the ground. But if you have less light getting through than what you normally would, then it's going to be cooler. So those block the sunlight. We get some CO2 release, so some carbon dioxide. Some CO2, some carbon dioxide is released. So that's a greenhouse gas. That tends to warm up the Earth because it traps in heat. But because we have more of the stuff that's reflecting the sunlight back into space, overall, it's going to be a cooling effect. So I'm going to say, but overall, is a cooling effect. I think I have a graphic with that, but I'm going to write down the last line and then go looking for it. So we get acid rain as well. I look for my last graphic. So they have evidence throughout history of these gigantic eruptions. So this doesn't fit that. This is 2001. You can see a picture here of Mount Pinatubo in the Philippines. And the temperature in degrees Celsius, so it's 0, so not changing much. We're almost a half a degree here, but we have temperatures doing this, the volcano erupts, and now you'll see it drops down almost a whole degree, so like 0.75 maybe degrees Celsius, so probably closer to 2 degrees, a degree and a quarter Fahrenheit. And then it comes back up again as those gases are dispersed out. But overall, looks like it brought down global temperature 1 degree Fahrenheit for 2 years. And they have evidence in like glacial cores and things like that of temperatures having dropped a ton more from these like massive volcanic eruptions. That's the notes. Thanks for sticking with me. Sorry it was long, but it was going to be long even if I was here. So hopefully this made it shorter and more tolerable. Hope you're doing great. See you when I'm back.